In just 7 days, the clock runs out. On March 16, 2026, 3I, Atlas will pass within 53 million kilometers of Jupiter. After that, it will continue its journey towards Saturn, Uranus, and Neptune before disappearing into the vast expanse of interstellar space forever. No human telescope will ever see it again. The opportunity to study this strange visitor from the stars will be gone. For the past 8 months, humanity's most advanced scientific instruments, Hubble, Webb, ALMA, SWIFT, SPHEREX, JUICE, Meerkat, the VLT, Gemini, and Rubin have been trained on a 2.6-kilometer object that came from somewhere far beyond our solar system. Now, as we approach the end of this historic observation window, we're left with a list of questions that remain unanswered. Where did it come from? We don't know. Why does it have jets perfectly separated by 120 degrees? We don't know. In which direction is it being pushed? NASA and an independent team have been in open disagreement about this for 6 days. Is Jupiter going to trigger something in it? We don't know yet. And there's the biggest question, one that no one in the mainstream scientific community dares to ask officially, but that a Harvard astrophysicist has been asking since July. This question still remains unanswered. In just 7 days, we'll have a chance to answer some of these questions, or at least to refine the answers we already have before the window closes forever. But for now, let's take a step back and do a full accounting of everything we know about 3I, Atlas so far. What has 8 months of careful observations revealed about this mysterious interstellar traveler? To begin, let's look at the definitive portrait of 3I Atlas. Discovered on July 1st, 2025 by the Atlas telescope in Chile, it is the third known interstellar object to pass through our solar system. Its eccentricity at 6.15 is the most hyperbolic ever measured for any object passing through our solar system. In simpler terms, this object is on a trajectory that takes it in and out of our solar system with incredible speed, far faster than anything we've observed before. Its velocity at infinity, the speed it would travel if it were no longer affected by the gravity of our Sun, is an astounding 58 kilometers per second. For comparison, the interstellar object Oumuamua entered our solar system at 26 kilometers per second, and Borisov came in at 32 kilometers per second. So, 3I, Atlas is nearly twice as fast as its predecessors. It's also incredibly old, estimated to be around 7 billion years old, far older than our Sun, which is about 4.6 billion years old. This object has been traveling through the cosmos for longer than our entire solar system has existed, and it's only passing through our solar system now. Its nucleus, 2.6 kilometers in diameter, was refined by Hubble after perihelion in January 2026. We know that it has a rotation period of 7.1 to 7.2 hours and an orbital inclination of 5 degrees retrograde, meaning it's moving backward relative to the planets in our solar system. But it's not just the size and trajectory that make 3I, Atlas, fascinating. The object's chemical composition is truly extraordinary. In August 2025, data from Webb and infrared spectroscopy reveal that the CO2 to water ratio on this object is 7.6 plus or minus 0.3, an anomaly 4.5 standard deviations above the normal cometary chemistry of our solar system. That's a 1-inch 300,000 chance that is consistent with normal comet chemistry. Furthermore, ALMA data from September and October 2025 showed that it contains methanol at 8% of its total vapor, 4 times the solar average for comets. This object isn't behaving like a typical comet from our solar system. In fact, it's been expelling water at 40 kilograms per second, which is an anomalously high rate at this distance from the Sun. By December 2025, Webb had detected methane deep in its interior, and its nickel vapor showed a nickel-to-iron ratio above the norm for comets in our solar system. Its morphology, revealed by Hubble in January 2026, includes 3 mini-jets separated by exactly 120 degrees from one another, and a fourth prominent jet pointing toward the Sun. Despite all of this data, we have yet to uncover any techno signatures. The Green Bank telescope, pointed at 3I Atlas in December 2025, detected no radio emissions, ruling out the presence of technological signals. So far, all evidence points to a natural object, but the nature of its behavior continues to raise questions. Now, as we count down to the flyby on March 16th, we are still left with so many unanswered questions. We know a lot, but the mysteries surrounding this object continue to intrigue and baffle scientists. 7 days remain until the moment of truth. What can we learn before this window closes forever? Stay with us as we dive deeper into what this flyby might reveal. Now, let's take a closer look at what we don't know. The most comprehensive analysis to date was published on February 28, 2026, by Federico Spada, Morata Krakowska, and Luke Dones. Their work analyzed 7,788 astrometric epochs, covering the period from May 2025 to February 2026, 10 times more data than NASA and JPL's official solution. Their conclusion was striking. The transverse acceleration, the sideways push of 3I Atlas, is comparable in magnitude to the radial component, which NASA had suggested was 5 times smaller. The difference between the two models lies in how the object's movement is interpreted. NASA's analysis suggests that the object is primarily being pushed away from the Sun due to the outgassing of volatile materials, a process typical of comets. However, Spada and his team argue that the acceleration is not purely radial. They believe that 3I Atlas is being pushed sideways, not just away from the Sun. The question that arises from this discrepancy is fundamental. If the object is indeed being pushed sideways, what does that mean for the forces at play? Could it be something beyond the expected cometary outgassing? We know that 3I Atlas has 3 mini-jets separated by exactly 120 degrees. This geometry could naturally favor a directional gas emission capable of generating a sideways acceleration. In other words, the object's unique jet system could be responsible for the observed sideways push. The regularity of the 120 degrees angle between the jets remains a mystery, one that standard cometary physics has struggled to explain. This is where the data from both NASA and Spada converge. Both teams agree that the jets and the object's acceleration are linked, but they offer different explanations. The question remains, is this a natural process or something more? The key to resolving this mystery may lie in the upcoming flyby of Jupiter. On March 16, 2026, 3I Atlas will pass within 53 million kilometers of Jupiter, the largest planet in our solar system. This encounter will provide a unique opportunity to test the models that disagree with each other. The object will pass through Jupiter's hill, sphere, the region where Jupiter's gravitational influence dominates over the Sun's. This area has a radius of about 53.5 million kilometers, and 3I Atlas will pass right at its boundary. This flyby is more than just a chance to observe a passing object. It's a real physical test of the models that have been proposed. The two different teams, the NASA team and the Spada team, predict slightly different positions for 3I Atlas as it enters Jupiter's hemisphere. This means that the geometry of the encounter will be different, which will lead to different gravitational deflections. And, crucially, these deflections will impact the object's trajectory after the flyby. By precisely measuring the object's position after March 16th, scientists will be able to compare these predictions and determine which model is more accurate. This may not fully resolve the issue, but it will provide a new constraint for both models, something that neither has had until now. There's more at stake here than just resolving a scientific debate. The flyby could reveal something unexpected. Jupiter's tidal forces, although relatively small at this distance, may trigger an outburst from the object. If this happens, it could expose new material from the object's interior, which has already shown signs of complex chemistry, methanol, methane, and other organic compounds. If the object undergoes a sudden eruption, it could provide valuable insights into the composition of its deeper layers. These eruptions, similar to the one observed in December 2025, would be a rare opportunity to examine the object in a completely different outgassing regime. The data collected from this flyby could be critical in understanding the object's internal chemistry and how it behaves under the influence of Jupiter's gravitational pull. In addition to the flyby, we also have data from the JUICE mission, which is currently en route to Jupiter. In late March 2026, the JUICE team will meet to discuss their November 2025 observations of 3I Atlas. These observations, combined with the flyby data, will give us a more complete picture of the object and its behavior. The scientific community is eager to see what the JUICE mission has uncovered, but there's one decision we have to address before we move on: the missed opportunity with the Juno spacecraft. In July 2025, 3 researchers, Loeb, Hibbert, and Kra, calculated that a small maneuver to adjust Juno's trajectory could have brought it to intercept 3I Atlas just 2 days before its flyby of Jupiter on March 14, 2026. This was not just a flyby. It was a close approach that could have taken Juno as close as 27 million kilometers to 3I Atlas. Juno, which was already in orbit around Jupiter, had all the necessary instruments for the job. Its infrared spectrometer, magnetometer, UV spectrograph, visible camera, and particle detectors could have provided an unparalleled view of this interstellar visitor. We would have had detailed images of its nucleus, close-range spectra of its coma, measurements of its magnetic field or lack thereof, and much more. The data from Juno could have filled in many of the gaps in our understanding of 3I Atlas. The problem? NASA never publicly confirmed that the maneuver was executed. Budget cuts under the Trump administration, concerns about Juno's remaining fuel reserves, and uncertainty about its mission end likely contributed to the decision not to adjust its course. As a result, Juno remained in its nominal orbit around Jupiter and will only observe 3I Atlas passively during its flyby. It could point its instruments at the object, but not from 27 million kilometers away, which would have provided a much higher level of detail. This was a missed opportunity, an opportunity to observe an interstellar object up close, not from hundreds of millions of kilometers away, but from tens of millions of kilometers. This window won't come again until the next interstellar object enters our solar system, which is impossible to predict. The Juno mission, designed to study Jupiter and its surroundings, could have given us the most detailed portrait of an interstellar object that we've ever had, but the decision was made not to act. Looking forward, we're relying on the JUICE mission to provide critical data. JUICE has been observing 3I Atlas since November 2025, using 5 different instruments to capture images and gather compositional data. These observations, which were delayed because JUICE was on the far side of the Sun, were received just last week. The teams are currently analyzing this data, and a meeting is scheduled for late March to discuss their findings. So, what are we expecting from JUICE? Several important pieces of data are coming from this mission. For example, JANUS, the navigation and science camera, captured more than 120 images of 3I Atlas. The composite image, which was published on March 2nd, shows the object with a bright, egg-shaped coma, a halo of gas, a long tail, and hints of jets and filaments. The full analysis will refine the size, morphology, and orientation of these jets as they were observed in November, just before the December eruption. In addition, MAJIS, the imaging spectrometer, collected compositional data from a distance of 66 million kilometers away. While the resolution isn't as high as that from Webb or ALMA, this new perspective is complementary. The instruments aboard JUICE were able to capture data from an angle that Earth-based telescopes couldn't, allowing for a different view of the object's chemistry. This data will help refine our understanding of the spatial distribution of molecules in the coma. The PEP particle detector also played a role in these observations, characterizing how the solar wind interacts with the coma of 3I Atlas. This interaction is particularly important for an interstellar object like 3I Atlas, which has a composition unlike anything in our solar system. The elevated CO2 to water ratio in its coma alters the ionospheric chemistry, which will allow scientists to test models that have previously only been theoretical. When JUICE's data from November is combined with the findings from Webb, ALMA, SWIFT, and SphereX, we'll have a more complete understanding of this object, but the March 16th flyby marks a crucial milestone. In the days and weeks following the flyby, the post-Jupiter astrometric data will provide new insights into the trajectory of 3I Atlas. This will be the first truly integrated picture of this interstellar object built from months of observations using a wide range of instruments. As we approach the flyby on March 16th, we're not just looking for answers about 3I Atlas, we're also looking at what this encounter has fundamentally changed in our understanding of the universe. Over the past 8 months, we've made significant strides in answering questions we never thought we could, and in the process, we've gathered data that will shape our understanding of the cosmos for years to come. But there are 3 major results from this encounter that go beyond just 3I Atlas itself. They have profound implications for how we understand life, the diversity of planetary systems, and the nature of interstellar objects. First, 3I Atlas has proven that prebiotic chemistry can travel across the stars, intact, over billions of years. This isn't just a theory anymore. This object has demonstrated it. When 3I Atlas arrived in our solar system, it carried with it a wealth of complex organic molecules, methanol, HCN, methane compounds, that are considered the precursors to amino acids, nucleotides, and sugars. These molecules survived 7 billion years of cosmic radiation, the cold of interstellar space, and the harsh environment of deep space. And when they interacted with solar heat, they were still chemically active. This provides observational evidence for something that, just a few years ago, was only a hypothesis, namely, that the building blocks of life can travel between stars. This means that the basic components necessary for life could be more common in the universe than we previously thought. While this doesn't mean we found life itself, it supports the idea that the essential ingredients for life could be spread across the cosmos, carried on objects like 3I Atlas. Second, the study of 3I Atlas has shown us that planetary systems around other stars can produce very different chemistry from our own. The CO2 to water ratio, the methanol concentration, the nickel content, all of these elements point to a planetary system that was colder and older than ours. 3I. Atlas was formed in a protoplanetary disk that had a very different chemical history from the one that gave rise to our solar system. This challenges the idea that all comets and other icy bodies share the same chemical signature regardless of where they come from. It's a clear indication that the universe is full of diversity when it comes to the chemistry of planetary systems. This leads to the third major result from this encounter. Interstellar objects are common. At least one object the size of 3I Atlas is in the inner solar system at any given moment. That means Earth was likely bombarded by interstellar objects throughout its early formation. The chemistry of 3I Atlas could have contributed to the building blocks of life here on Earth, not as a metaphor, but as a measurable physical inference. These objects have been traveling through interstellar space for billions of years, and now, thanks to 3I Atlas, we have the data to show that these objects are not anomalies. They're part of a much larger population. Before this encounter, the idea that interstellar objects were a common occurrence was largely speculative, but the detection of 3I Atlas, along with the population estimates based on its trajectory, has now changed that perspective. These objects could be a regular part of our cosmic neighborhood, and their impact on the evolution of life on Earth and potentially elsewhere could be more significant than we ever imagined. While all of these results are groundbreaking, they still leave us with one unresolved question. Is 3I Atlas a purely natural object? This question has divided the scientific community. The observations are consistent with a natural object. No single piece of evidence points to an artificial origin. However, the sheer number of anomalies associated with 3I Atlas is hard to ignore. The perfect symmetry of its jets, the strange alignment of its orbit, and the high probability that it passed within Jupiter's Hill sphere at just the right distance, these are all details that do not have easy explanations within the standard framework of cometary physics. Loeb, the scientist who has been tracking these anomalies, has listed 15 to 16 separate features of 3I Atlas that seem improbable or unexplained by natural processes. Each one of these anomalies could have a natural explanation, but taken together, they present a statistical puzzle. Can a single object accumulate this many simultaneous anomalies by pure chance? The symmetry of the jets, for instance, is not something standard cometary physics predicts. While it's possible for natural forces to produce something that looks like this, the specific configuration of the three jets at exactly 120 degrees is highly unusual. The probability of 3I Atlas passing through Jupiter's Hill sphere at the exact distance it did? That's a 1 in 26,000 chance. The CO2 to water ratio? It's 4.5 sigma out. The methanol enrichment is 4 times the norm. And the non-gravitational acceleration, which NASA and Spada's team measure differently, still doesn't fit perfectly with either model. So, while there's no direct evidence to suggest 3I Atlas is anything other than a natural object, the sheer number of unexplained anomalies makes the question worth asking, could it be something more? As we count down the days to the March 16th flyby, we are left with many more questions than answers. Will the flyby provide the data that will clarify these anomalies? Or will it leave us with more questions than we had before? Either way, one thing is certain. The window to study 3I Atlas is closing fast. In just a few short days, this interstellar traveler will pass beyond our reach, and with it, the chance to uncover the final mysteries it holds.